Hello, calculus students and anyone who seeks the truth. Welcome to the lesson on definite integrals and its properties. And in this lesson and these next few videos, we're really going to talk about approximation methods more so than the exact answer. And then in the next set of videos, we'll discuss how to find the exact answer to some of these integrals. So first, let's begin and understand a little bit more about the definite integral and what it really is. So this is some important notation here. So this is really the area between f of x and the x-axis. So this expression is equivalent to, let's say this function here is f of x. Then this is the area underneath the curve between A and B and the x-axis. Okay. So this area is exactly equal to this. Okay, so that's what this is asking for. This is just a little bit of notation. This dx here is essential. It's often forgotten, but it is essential because it indicates what is the variable here. So for example, if I have a complicated expression like the integral from a to b of 3k squared plus 2e to the kx, if I don't write dx here, we don't really know whether we're integrating with respect to x or with respect to k. Okay? So this little dx here indicates clearly whether we're talking about x or we're talking about k as the variable. Because this integral and this next integral that I'm about to write, 3k squared plus 2e to the kx, if I write dk, that means k is the variable, okay, and x is the constant. So there's a significant difference between these two. For those of you who are taking AP Calculus, if you omit this dx, or if you write in the wrong dx, you will likely lose points on whatever question that you're currently answering. More importantly, later we'll see that this dx and dk, or whatever variable it is, this little part right here, has actually some very significant properties, and it's used for other things besides just indicating what is the variable. Okay? So it's essential because it indicates the variable. And later on, we'll see some other good uses for this differential, this dx or dk or du or whatever it is. Okay? So, like I said before, in this lesson, we're going to focus on approximation methods. We'll deal with the exact answers a little bit later. And the approximation methods here, there's basically 4 of them. The left sum using left side rectangles, the right sum, the trapezoid sum, and the midpoint sum. And just a little bit of notation here. We usually write this as L of n, R of n, T of n, and M, big M of little n, okay, where n is the number of subintervals. Okay. And these subintervals, some are often evenly spaced, but they do not have to be evenly spaced. Okay, so this is the notation that's often used. It's not every book, not every test will use this, but this is the most common one that is used, and we're going to stick to it pretty consistently here in my class. Okay. Also, I should say that there's a special term. This is the Riemann sum, and it usually captures all 4 of this plus some other ones. So it's named after Bernard Riemann, a great mathematician who used these sums to start doing some approximations, and he was able to use these sums to get some exact answers. So this is often called, this L right here is often called the left Riemann sum, the right Riemann sum. I don't really hear the trapezoid used that Riemann sum, use that very often, or the midpoint. So this is very common to hear, like the left Riemann sum, right Riemann sum. And I'll explain a little bit more about the difference, the subtleties in the Riemann sum versus the trapezoid, the midpoint, and some of these other things later on. Okay, but we just want to get, right now I just want to get all the notation and all the technical terms out there, so you guys have a better sense of what's going on, better way to communicate. Okay, so I'll end this video here. In the next video, we will talk about how to use these sums to do some approximations.